name is Sarah.
My name is Cameron.
Adam. Eric.
And we are electrical engineering students here at York University.
That's it?
The embedded system is made up of both hardware and software. The system is made up of three basic components: a sensor to receive the input, a microcontroller, which is the main part of the system which will run the software, and an actuator, which will respond to the signal. For example, when a car is going into a parking lot, the gate will sense it and it will open. Embedded systems are important because they can be used in almost everything we interact with in our everyday lives, from our phones to our computers to our kitchen appliances or even our cars.
This year we took a course called EECS 3215, which teaches us about the purpose, design, and operation of embedded systems. As electrical engineering students, it's important that we learn about embedded systems because we will be interacting with them in our everyday lives. Over the past 3 months, our goal was to build a frontal ECG, which measures a person's heart rate. To do that, we place a pad on the wrist here, and the bottom of the leg to measure the potential.
And the electrical activity of the heart over a period of time. When the heart expands and contracts, the sinoatrial node in the right atrium carries an electric signal to the left atrium and to the upper ventricles. This electric signal propagates towards the skin at the order of microvolts, to which an electrode will measure the voltage with respect to another limb given by Enthoven's triangle. Our ECG uses the Arduino Uno as a microcontroller. It has an LED flashing every time someone's heartbeat beats, as well as a 4-watt speaker that beats every time it pulses. It also computes your heart rate and the local average of last 10 periods, and it will show it on the LCD's display.
In order to perform a frontal ECG trace, we have our 3 electrodes. So basically what we've got are a little adapter that we've made out of a headphone jack and a piece of copper wire. And we feed that through a headphone cable, your standard auxiliary cable, into our headphone jacks on the breadboard. So the way this works is that we have one connected to the left leg as your ground, and then you have one terminal connected to your left arm and one to your right arm. The signal from our left electrode comes through this terminal from our right electrode and our grounding leg. Right after the signals come in, they go through decoupling capacitors and then a 100K resistor to ground so we can get rid of our bias currents. Then we go through a INA 128 operational amplifier, and this is where we gain up our small signal quite considerably, and we have a resistor of 10 ohms connected here. And now this is where we take the V out from our operational amplifier to the Arduino. Another important component that I didn't mention was this, and that's an LM324 operational amplifier. Essentially what we're doing is making a source follower so that we can remove the loading effects caused by the ground, so just to make sure that we don't affect our INA 128 operational amplifier. So that's it for the analog part. Now we're going to move over to the Arduino. Our Arduino takes the V out from our amplified signal and samples it 1,000 times a second. Then, based on the values that we receive, we can determine when to turn on the light, which will flash when we have a heart pulse, and also we make a sound with our speaker that signifies that a heartbeat has been made.
Demonstration of our project is as follows. So the electrodes are attached to Cameron's palms and his leg, and as you can see over here, the LED is flashing for every pulse that's going on. And then there's also a speaker that beeps at every pulse. And then up here you can see that it shows his heart rate, and you can see the peaks of it.
So now we're going to talk about some of the issues we encountered while building this ECG. So one of the main things was the interference. So all of the electronics in this room are powered by 60 hertz electronics, and we were getting a lot of interference. So to avoid that, we put a very, very strong ground. We shortened the wires, and we also are going to add shielding eventually.
With respect to the op-amps, it introduces a biasing current that could charge up the decoupling capacitors. So by introducing a ground to the other side of the decoupling capacitor, it allows the bias current to flow down.
So this concludes our presentation. Thank you for watching, and we all want to be electrical engineers one day. Thank you.